In this pre-lecture, we're going to talk about Fermat's little theorem and a generalization of this, which is Euler's theorem. So Fermat's little theorem we talked a little bit about at the end of class on Wednesday, and then we'll generalize that with Euler's theorem. So the statement of Fermat's little theorem is let p be a prime number, then for any integer x, x to the b is congruent to x mod p. So any integer raised to the pth power, we just get that base back again. So to prove this claim, to prove this theorem, we first need to prove this claim that for I between 0 and p, not including 0 and p divides the integer p choose I. So recall that p choose I is p factorial over I factorial times p minus I factorial. And then to make this, well, the idea here is that the p on top won't cancel out with anything on the bottom. But to make this rigorous, what we're going to do is multiply I factorial p minus I factorial over to the other side. And so we've got that equals p factorial. So then, since p is prime, p doesn't divide I factorial, since I is less than p, and p does not divide p minus I factorial, since, I'll move this up a little bit here to give some more space, since p minus I is less than p, so we must have p divides p choose I. Alright, so now that we've shown that p divides the integer p choose I, we're going to use the binomial theorem for expanding these binomial products, and use that to show that for integers x and y, x plus y to the p is congruent to x to the p plus y to the p mod p. So looking at x plus y to the p, that's x to the p plus p choose I, x to the p minus 1, y to the 1, plus p choose 2, x to the p minus 2, y squared, and so on up to p choose p minus 1 times x to the 1, y to the p minus 1, plus y to the p. We're looking mod p. And now, since p divides each of these p choose I for I between 0 and p, those middle terms will all be congruent to 0 mod p. So plus 0 plus 0. So this is since p divides p choose I, p choose I is congruent to 0 mod p. And so then that's getting rid of those zeros, x to the p plus y to the p mod p. Alright, so we've proved those two claims, but we're not done with the proof of Fermat's little theorem yet. So to finish this up, we're going to use induction on x to first show this for non-negative integers x, and then at the end we'll finish this up for negative integers to complete the proof. Alright, so for induction, we're first going to establish our base case. So if x equals 0, then x to the p is 0 to the p, and that's just 0, which was x. So we have x to the p is congruent to x mod p, so that gives us our base case there. So now we're going to assume that x to the p is congruent to x mod p, and then look at what happens with x plus 1. So we want to prove that our statement is true for x plus 1. So x plus 1 to the p, by the claim that we just proved, that's congruent to x to the p plus 1 to the p mod p. So this is by our second claim. And then x to the p is congruent to x by assumption, and 1 to the p, 1 to any power, is 1. So we've got x plus 1 mod p. So this is x to the p is congruent to x by assumption. And so we've got x to the p congruent to x plus 1 mod p. So that completes the induction. So we have x to the p congruent to x mod p for all non-negative integers x. So now we just need to deal with the negative case. So if we have this as true for some non-negative integer x, and then we look at minus x to the p, this is going to be minus 1 to the p times x to the p, which is going to be, if p is odd, then minus 1 to the p is minus 1. If p is even, then we know that the only even prime is 2. So then minus 1 to the 2, that's 1, but mod 2 minus 1 is congruent to 1. So either way, we end up with minus 1 times x to the p, and x to the p is x for non-negative numbers, so x non-negative, so we already showed that. And so this is minus x. So this completes the proof by showing it's true for negative numbers, negative integers as well. So this completes the proof. Alright, so this is kind of a cool fact, but maybe it's not so clear at this point why we should actually care about this. So we just showed that x to the p congruent to x mod p for all integers x if p is prime. And if x and y are relatively prime, then we have that x inverse exists. So we can start with that x to the p congruent to x mod p, multiply both sides of this by x inverse, so you got x inverse x to the p is congruent to x inverse x mod p. So then x to the p minus 1 is congruent to 1 mod p. So this is starting to look kind of interesting here, that we've got some power that no matter what we're raising x to, or raising to that power, we're getting 1. And then what we can use this for is we've got x to the p minus 1 congruent to 1 mod p. If we split off an x from that, we've got x to the p minus 2 times x is congruent to 1 mod p. So this means that x to the p mod p minus 2 is the multiplicative inverse of x modulo p. So this can be a really handy way to find multiplicative inverses rather than just trying every integer relatively prime to our modulus to see if it works. So for example, if we're finding the multiplicative inverse of 2 mod 11, we know that 2 to the 10th is congruent to 1 mod 11. So then 2 times 2 to the 9th is congruent to 1 mod 11. So 2 inverse is 2 to the 9th, and working out what that is, we get 6. And then you can double check that 2 times 6, that's 12, which is congruent to 1 mod 11, so that is, in fact, a multiplicative inverse. So this can give you a way to find multiplicative inverses just by taking powers rather than doing a bunch of different multiplications. So this can be handy for that. This is also useful for some stuff to do with primitive roots. So we'll talk about that a little bit later once we talk about group theory, since that'll be a little bit easier to work with then. So it's important to remember here that what we just said only works when p is prime. However, we can generalize this. So we'll have to generalize this using something called the Euler phi function. So for a positive integer n, the Euler phi function, phi of n, is the number of integers b such that 1 is less than or equal to b is less than or equal to n, and the greatest common divisor of b and n is 1. So we're counting how many things relatively prime to n there are between 1 and n inclusive. Since we're looking at things that are relatively prime to n in that range, that's going to be the same as just counting the number of elements in z mod n cross. So that's number of elements in z mod n cross. So how many integers there are in z mod n which have multiplicative inverses. So for example, if we're looking at phi of 5, then we're looking at the size of z mod 5 cross there, that group of units. So listing everything in there, we've got 1, 2, 3, 4. So that's 4 elements. Looking at phi of 9, we've got the number of elements in z mod 9 cross. So things relatively prime to 9. We've got 1, 2, not 3, 4, 5, not 6, and 7, and 8. So that gives us 6 elements in there. For phi of 11, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that gives us 10 elements. For phi of 15, we're looking at 1, 2, not 3, 4, not 5, not 6, 7, 8, not 9, not 10, 11, not 12, 13, 14, which should give us 8 elements there, if I didn't miss anything. That's how we compute the Euler phi function. And notice here that if p is prime, that when we're looking at things between 1 and p relatively prime to p, that's going to be everything except for p. So that'll be p minus 1. And we saw that, for example, when looking at phi of 5, that was 5 minus 1, which is 4, and phi of 11 was 10, which is 11 minus 1. Those are prime, so we can see that that's true there. So then the generalization of Fermat's little theorem for all numbers n is that for x relatively prime to a positive integer n, x to the phi of n is congruent to 1 mod n. So for a proof of this, you can see the book. And then for the specific case when p is prime, this says that x to the phi of n, so when p is prime, that's just going to be p minus 1, is congruent to 1 mod p. And then if we multiply by both sides of that by x, then we're getting back to sort of our original statement for Fermat's little theorem. X to the p is congruent to x mod p. So similar to Fermat's little theorem, we can use Euler's theorem to find multiplicative inverses, but keep in mind that we need to be working with the Euler phi function rather than just doing the modulus minus 1. So for finding the multiplicative inverse for 2 modulo 9, we would use that phi of 9 is 6, which we worked out on the previous slide. So then by Euler's theorem, we know that 2 to the 6th is congruent to 1 mod 9. So that means that 2 times 2 to the 5th is congruent to 1 mod 9. So 2 to the 5th is going to be an inverse for 2. And 2 to the 5th works out to be 5 mod 9. And we can double check that 2 times 5 we get 10. So that's congruent to 1 mod 9, and that really is a multiplicative inverse. So this can give us a handy way to find multiplicative inverses rather than checking sort of everything in the multiplicative group. Using Euler's theorem can also be handy for finding really large powers, because remember, if we've got x to the phi of n is congruent to 1 mod n, then sort of a lot of this stuff is going to collapse into 1. So I'll show you what I mean by that. So for 2 to the 38th mod 9, so once again we're working with a modulus of 9, so we're using phi of 9 equals 6. So we still have 2 to the 6th is congruent to 1 mod 9. So now when we look at 2 to the 38th, we can split off basically chunks of 6 2's. So we can write this as 2 to the 36th times 2 squared, and then that's going to be 2 to the 6th to the 6th. So I hope you remember your rules for exponents. And then 2 to the 6th by Euler's theorem was congruent to 1. So we've got 1 to the 6th times 2 squared. Sorry, this is all mod 9, mod 9, mod 9. And so then we just get 1 times 4. And so we end up with 4. So we can use this to compute large powers much more efficiently than trying to multiply out 38 2's here. So for now we're done with chapter 6, although we will most likely cover Sunzi's theorem later, and we'll talk about primitive roots a little bit more later as well. On Monday we're going to start group theory. So because group theory deals with a lot of stuff with sets and functions, it would be worthwhile to review the material from chapter 1 on sets and functions if that wasn't very comfortable for you when we covered that. Alright, so this is it for this pre-lecture, and make sure you answer those questions.